Hello, everyone. My name is Israel, and I am the project leader of Team 25. For this program, we were assigned on a mission, and in the presentation, we will introduce ourselves and present the work each of us have done on our PDR.
Hello, my name is Charles Sleeper. I am on the science team on L-Space Team 25, and I guess it's my job to explain to you about how we split up into our different sections. We split up into 3 groups primarily because we were such a small team. There was about 9 or 10 of us at the beginning, and so we split up into a science team, a budgeting team, and an engineering team, each doing their own part. Having a small group like that really enabled us to get a lot of work done instead of having a big old hierarchy with different titles and such like that. So that's pretty much all I have to say.
On the mission overview, we have the descent and landing, the payload development, and science experiments.
Right. Hello, my name is Jacob Miller. I'm the science team coordinator, and here we have our section 2, the evolution of a project. Early on, we decided we would let the descent and lander dictate the rest of the criteria. So once we learned that the descent and lander would weigh about 2 kilograms, we then decided the payload had to be under 3 kilograms to fit our mass constraint of 5 kilograms total. We allotted 1.5 kilograms for instruments and another 1.5 kilograms for the rover. The design went through many iterations, but as the time went on, the criteria stabilized. And our science experiment developed as the payload developed. As we changed instruments, the science experiment also had to change. And now we'll head over to section 3, our science value. So for our science objectives, we needed to determine ice exists. We need to determine the ice depth. We need to determine the chemical composition of the ice. Is it H2O or CO2? And we need to determine the potability of water ice, if it is water. And we need to determine the quantity of ice. These are important because this ice is a candidate for feedstock for future Mars manned missions.
So for our landing site selection, we were looking for an area that had the highest possibility of ice being present. So as you can see in this chart here, these are the criteria we used to look at different landing sites. We looked at 3 main sites: Moreau Crater, Detronalis Mensae, and the McClown Crater. We ended up choosing the Moreau Crater because it fit most of the criteria that we had come up with. One of the main reasons that we chose it is looking at that image there. If you see all the tiny little bright blue dots, those are possible glacial sites. And then the dark purple dot in the top left is a possibility for presence of hydrogen minerals. So basically, there's a high possibility that there's ice here. In addition to that, there are some outside literature sources that we looked at that suggest that because of the geography of the Moreau Crater, there are signs of glacial movement there. And it is hypothesized that most of the glaciers originated at the tip of the Moreau Crater. So that is yet another reason why I wanted to choose it. In looking at all these, you can see the criteria listed that we used. The main criteria is all about the landing information, so knowing that there's a flat area we can land on, the presence of water, which was one of our mission requirements, and as I was talking about earlier, there's evidence of different possible aqueous processes. And then there's also an easy landing site where a future crewed mission could set up camp on Mars. And the last section there is just knowing that there's an area that would be able to support the probe if it actually landed on it.
One of the instruments we have on board is the APXS. It has 2 modes, X-ray and alpha particles. One thing we're particularly interested in is the alpha particle spectrometer. It can analyze the difference between elements, so it can tell the difference between carbon and oxygen, which is very important for knowing if it's carbon dioxide ice or H2O ice.
So for our preliminary experiment, as was previously mentioned, one of the things we want to look at is making sure that the instruments actually work. For the experiment for testing the water ice versus dry ice, we're going to do 2 main experiments. One, we're going to do an experiment in a laboratory setting where we will look at frozen CO2 ice, dry ice, and then frozen pure water ice, both deionized and then regular. And then we will also look at water ice that's had various toxic elements injected into it. And the levels for those various toxic elements that will be injected into the ice will be based off of real life scenario. And elements were chosen because 1, they're toxic, and 2, they're actually found in the Mars environment. And then the second part of the preliminary experiment will be going to somewhere that actually has glacial ice, and then testing the APXS and the GPR instruments out in real time to make sure that they work here on Earth. So if they don't work here on Earth, they're not going to work on Mars.
All right, so I'm Travis, and I was in charge of the entry, descent, and landing, or EDL systems of our Mars lander. The EDL can be broken up into 3 subsystems: the heat shield system, the parachute system, and the airbag system. So once we disconnect from the orbiter, the lander will be on a course to the surface. Upon entering the Martian atmosphere, the heat shield will redirect and absorb the heat energy of atmospheric entry. We designed the heat shield to include a trio of fins to allow the lander to slowly spin, which will evenly distribute the heat and allow for aerodynamic stability. Once we reach an altitude of about 10,000 meters, the lander will be traveling at a velocity of about 625 meters per second. At this time, we will both deploy the parachute and attach the heat shield. The lander will continue to slow down under the drag of the parachute to a velocity of about 200 meters per second. At about 505 meters above the surface, the auxiliary rockets will fire, slowing the lander down to 0 meters per second at about 20 meters above the surface. At that moment, the lander will disconnect the parachute and it will fly under the power of the auxiliary rockets out of the way. The airbags will be deployed at the same time as the parachute is released. They will provide the lander with a soft landing by extending the time it takes to decelerate on impact, thereby lessening the kinetic energy absorbed by the lander. After bouncing a few times, the lander will come to a rest. We'll give the airbags time to fully deflate before the first door opens. If the lander happens to land on its side, the opening of the first door will flip it upright. And then once all 3 doors are open, the rover is free to proceed on its mission. By looking back at past missions, we were able to learn from their successes and using existing proven technologies to create a reliable, inexpensive lander. From the airbag designs of the Viking landers of the 1970s to the parachute technologies of today, we took and modified the best parts to create our lander to accomplish our mission.
All right, now moving on to section 5, our payload criteria.
Hi, my name is Mariah, and here we have the payload system rover. And the design came from one of our teammates named Johnson. He came up with the criteria of the rover and how it should look. And so pretty much I did the drafting and SolidWorks, and pretty much the rover has, you see the drivetrain, you see it has a camera, an electric box, and the back there where the holes are is a solar panel, and it has batteries, and also has a visual system in there as well. And it's inexpensive, and pretty much I drove it where it's moving in motion.
And now we'll go over the instruments for our payload.
One of the main instruments we chose was called the Alpha Proton X-ray Spectrometer. We are inheriting this instrument from previous missions. The main purpose of this instrument will be to determine the chemical composition of the sample. It's lightweight. The instrument is going to accomplish 3/5 of our scientific objectives. And then in addition to that, it is also low power.
Next up, we got the Mini Ground Penetrating Radar, or MGPR, weighing in at 0.045 kilograms. This is an excellent device for our small criteria. It was developed relatively recently, and it uses radio waves to report the composition of crust underneath. It's got great resolution, up to 15 centimeters at distances under 5 meters. It's, as we're in section 2 of Mars, where there's discontinuous shallow ice within 5 meters of the surface, it's perfect. We expect to find ice that shallow where we're at. This also may allow the payload to maneuver where ice is. This device does accomplish 2/5 of our scientific objectives. It lets us know if there's ice, and it lets us know that how much is there.
So the next step that we needed in addition to the instruments was designing a visual system. For our visual system that I designed, it's primarily made of Raspberry Pi and Arduino components. The reason for that is that all these are commercially available. You can buy the parts off Adafruit or Amazon. It's inexpensive and it's easily configured.
All right, now we have section 6, our activity plan. Briefly, you see our budget here. We're under 15 million, so if there are any errors, we're confident that we have the wiggle room to add any unforeseen costs we may need.
Hello, I'm Declan Krigo, and talking about the public outreach. So the first thing that we're going to do is actually just go out at our universities and colleges. We can communicate with a lot of different people in a lot of different fields. And then the second thing that we're looking at doing is actually just setting up a social media platform for us to get very popular very quickly. And instead of focusing on getting our own popularity and our own following and things like that, we're actually going to use pop culture and popular science within social media to go ahead and piggyback off of other people's fame. And that has the ability to get us a lot of popularity very quickly for very little cost. This is a low cost option with a very high volume potential.
Finally, we have our conclusions section.
So just to summarize our project, we began by investigating the different atmospheric forces that the probe would face as it was entering the atmosphere. After that, we were investigating what would happen when the probe would land. Then after the probe had landed, we investigated on how we were going to deploy the payload. And then, of course, within the payload are the scientific instruments, so we had to determine how those were going to deploy. And then after that, we would, of course, conduct a scientific experiment, assuming our probe actually made it to Mars. We would then analyze the data, and all of this would be to add to human knowledge of Mars and to give us more information for future HLS-2 missions and decide if the Moreau crater could serve as a viable candidate for ice.
All right, that's all we had for you. So long, and thanks for all the fish.